let's take a look now at this problem of thick shells where the wall thickness is being asked. The problem says that, calculate the thickness of the metal necessary for a cylindrical shell of internal diameter of 160, and let me mark it here, 160. Well, actually it's already set up in here, 160 millimeters, which is this one that I'm already written here, to withstand an internal pressure of 25 megapascals, being the maximum permissible tensile stress 150 megapascals. Good. So let me check something first about the data of the problem. Now the data was given as 125 megapascals, not 150 megapascals. All right. Let's check the data to see what we got. So we got the internal pressure, which is equal to 25 megapascals. We have the, I'm going to put it like internal radius, that is 80 millimeters in this case, because we're given the diameter of the internal part of the cylinder. Then we got the maximum permissible tensile stress. Now, when we talk about thick shells, we know that the largest stress we're going to get there is the circumferential stress, the Hooke stress there. So meaning that I'm going to write like this: the maximum permissible circumferential stress is going to be 125 megapascals. It means that we need to work just with the description of this stress, the definition of this stress, to find out how much is the value of the thickness. And I'm going to mark as T, the thickness, knowing that the thickness is defined as the difference between the outer radius minus the inner radius. We don't have the outer radius, and we need to get it then first from the formulas. I have written here on the left, the formula for the circumferential stress in the particular case where there is only internal pressure and we're talking about the maximum circumferential stress. So if I bring that down here, so I'm going to have that this sigma circumferential, or the circumferential stress maximum defined by this formula. This is just taking into account, for example, that from formula 1, from this equation here, this equation 1 here, we're considering that there is no external pressure and the radius equals the internal radius. So that's it. That's why it resolves to this part here. So we're going to have that this equals to this, and then this is going to multiply these two terms here, and these are going to divide the difference of the square of the terms multiplied. So this is a pretty simple problem, and the only thing to do is to substitute all the known data and then solve for the unknown data, and kind of using just this formula, and that's it. So let's do it. So the maximum circumferential stress is going to be 125 megapascals. Actually, let me get rid of this because this is the units are going to match perfectly. So I'm just not going to write it this time. So internal pressure is going to be 25. That multiplies this fraction here, which is it's going to be non-dimensional. That's why I'm not writing the units along. I'm going to have here then 80 squared plus RO squared divided by the outer radius squared minus 80 squared. Then let's just solve for the outer radius. I'm going to then multiply this denominator to this 125, and I'm going to keep things simple. So if I multiply this whole thing here to the 125, I'm going to get 125 times RO squared minus 125, and multiplies like this. I'm going to keep it working like this. I'm not going to substitute any value yet because of convenience at the end. We're going to see why. And this equals to what is left. I'm going to just multiply that once. Square plus 25 outer radius square. Now I'm going to put outer radius to the left and then the rest of the terms to the right. And when I put the 25 or transfer the 25 to the left from the right to the left, this is going to end up being this one here. And then when I transfer the 125 from the left to the right here, this term here, this is going to end up doing 150 times this much Then if I want to solve for this, it's going to be as simple as just leaving this outer radius alone. And I'm going to have this one here. It's going to be 150 times 80 squared divided by 100. Perfect. Which can be simplified to square root of 1.5 times 80. That's why I didn't take the square of 80 at the beginning. Then the outer radius, if I do a quick calculation, that's going to be, pull up the calculator here, 100 and so square root of 1.5 times 80, that's going to give me 97.98, very close to 80. Sorry, very close to 98. Let me write it better. Very approximate close to 80 millimeters. Then it means that if I come back here, T, that is the difference between the outer radius, that is 80, we have just found, minus the inner radius. Sorry again, this is 98. 98 approximation minus 80 is going to give me that the thickness according to these parameters needs to be at least 18, right here, 9 millimeters. And this is the whole problem. That's it. No more than this. Pretty straightforward, a little bit of substitution and mathematical operations, but in the end, it's very straightforward.